So in Chapter 5, we're looking at probability. We're going to start today just by learning some of the basic probability rules. This first section is so important. The foundation of the concept of probability is going to be really important for trying to help us solve more complex probability questions. So throughout this chapter, you will hear me ask all the time, back to the basics, how do I find probability of an event? So that's something that we're going to talk about today. Probability is the chance of an event occurring. A probability experiment is a chance process that leads to well-defined results called outcomes. An outcome is the result of a single trial of a probability experiment. And the sample space is the set of all possible outcomes of a probability experiment. We write it using these fancy braces because this is a set of outcomes, and we separate the events with a comma. So let's practice writing sample space for the following experiments. Rolling a die once. So the sample space is going to be the set of all of the possible outcomes when you roll a die one time. Okay, so 2 and 3 are 2 possible outcomes. What's the first one that we might list?
1.
1. When we're referring to a die, unless otherwise noted, assume that it is a 6-sided die. Flipping a coin once. Good. How about flipping a coin twice? The experiment has now changed slightly. The experiment is not flipping a coin once and recording your outcome. The experiment is flipping the coin twice and recording your outcome. So just let's chat about this for a second. What's one possible outcome if you were to flip a coin twice? You get heads on both flips. You get 2 tails. So what we're seeing here is that an outcome is no longer just heads or tails, but the result of both flips. The experiment is the outcomes for 2 flips of a coin, not just the flip of a coin, okay, and we're doing it twice. Every trial is going to be 2 flips of the coin. So every single one of us could potentially flip a coin twice, and we would all have our own outcome. Now, the possible outcomes that exist, we talked about heads, heads. We also mentioned tails, tails. Heads, tails.
Tails, heads.
Tails, heads, good. Flipping a coin 3 times. There's a really nice way to do this methodically, but let's start with considering, all right, I'm counting the number of heads that I can get. So what is the maximum number of heads that I could get when flipping a coin 3 times? 3 heads. Are there any other ways that I could flip a coin and get 3 heads? No. So now let's decrease the number of heads to 2. How many ways could I get 2 heads? Heads, heads, tails.
The tail head, head.
Tail, heads, heads.
Tail head. Or head, tail head.
Good. Now, I'm a big pattern fan, and I feel like patterns help me keep track of things. So the reason why I didn't list the outcomes that Maddie gave me the way that she did was because I'm using this setup to help me keep track of my outcomes. When I ask you to list the sample space, I'm not asking for some of the outcomes, but all of the outcomes. So we need to be able to keep track of that. Foreshadowing, we're going to learn another way to do that. But so I started with my 3 heads, and then I was like, okay, now let's do 2 heads. So I started with the obvious of just getting 2 heads first and then a tails. So there's always going to be 1 tails in the 3 flips, right? Watch where my tail moves. Started last flip, then it was the middle flip, then it was the first flip. Now this isn't the be-all, end-all way of organizing this, but if you're able to recognize these patterns and come up with some systematic way for listing these outcomes, you're less likely to forget one. Are there any other outcomes that result in 2 heads and 1 tail? Okay, so now let's decrease again the number of heads. We looked at 3, 2, now let's look at 1 head. What are the possible outcomes if I have exactly 1 flip landing on heads? Heads, tails, tails. Guys, look at the movement of the flip that lands in heads. It allows me to see that pattern. It allows me to keep track of all of those possible outcomes. Are there any other outcomes that result in 1 head and 2 tails? Okay, so again, decreasing the number of heads to 0 heads, that means we have 3 tails. Questions? Drawing a single card from a deck of 52 cards. We're not going to list this sample space out, but I do like this example because I think it's important for us to review the construction of a deck of cards. If you don't play a lot of cards, you may not be super familiar with a standard deck of cards. After this example, we're going to consider it common knowledge. Okay? So we have a deck of cards that has 52 in there. What are some ways that we divide that deck of cards? What are those called? Suits. Suits. And how many are there? 4. There are 4 suits. Sorry, what were they again?
Hearts, diamonds, clovers, and I don't know.
Spades.
Good. Hearts, diamonds, clubs, and spades. Do you guys remember the shapes for these? Hearts and diamonds are pretty straightforward. What does a club look like?
Clover.
I always call it puppy dog, but.
Really?
Yeah.
It looks more like a clover.
I mean, I don't know. I like puppies more than clovers, so I always call it a puppy dog theme. And what about a spade?
Like an upside down heart?
Yeah, kind of like an upside down heart with like a stem.
Yeah.
So,
A mushroom?
no, kind of like a mushroom. I don't know. Anyway, we're not going to give you the shapes, but, you know, in case you were wanting to learn more. What's another way that we can differentiate or separate or divide the cards?
By color.
By color. What are the 2 colors in the deck?
Red and black.
Red and black. Now, is there any special division of the red and black? Yeah,
Hearts and diamonds are red and clubs and spades are black.
good. Which means that there are how many red cards and how many black cards? How many cards are in each, oh, Kaylee, yeah, question?
Is this excluding or including the Joker cards?
We do not include the jokers at all. Good question. How many cards are in each suit?
13.
There's 13 cards in each suit. What are those cards?
Ace through 10, Jack, Queen, King.
Kaylee, what did you say? How'd you start?
Ace through 10.
Okay, so 1 through 10. So this is always really interesting. I love this debate because there's always this question of, is ace high or low? Ace is 1. Have you ever, if you look at a deck of cards and you're looking at like the number cards, like the 3 of hearts has 3 hearts on it. The 7 of hearts has 7 hearts on it.
Yeah.
How many hearts is on the ace?
1.
But in a lot of
games, it ranks high.
I think it's up, I mean, I realize that certain people play certain rules, and that's, I mean, that is how it is. I'm just saying, I always think it's funny that there's ever been a discussion of whether or not ace is high or low. It is, like, it's 1. 1, that's it. Yeah.
Are you saying that because there's a heart in the middle? Because technically there's really only one on the king, queen, and jack, then?
I don't think there's any hearts on the jack queen. Maybe on their outfits?
Isn't this big coin?
No. I don't know, maybe. Not really the point. I'm not gonna ask you guys about playing cards. But, I just, when I list them out, I always put ace first, and then we always have this conversation, so I think it's fun. So we've got ace, 2 through 10, jack, queen, and king. A lot of times we refer to face cards or picture cards. What cards are those?
Ace, Jack, Queen, King.
Just jack, queen, and king.
Oh, really?
Ace is not a face card. There's no face on it. There's no picture on it.
Yeah.
I mean, it's not an I win. I'm just making sure that you're well aware so that when a question shows up on my stat lab, like, what's the probability of getting a face card? You know what cards they're referring to. Questions? Again, if you're not familiar with a deck of cards and how it's constructed, you probably want to study this. After today, we're going to consider common knowledge. So I'm not going to give you this information on a test. You need to know it. If you're like, yeah, this is not something I've done, start playing solitaire. You'll get familiar with the deck of cards real fast. And then you'll get really addicted to it. I got really into solitaire for a period of time. So much so that, like, I was dreaming about solitaire and, like, strategy. And I don't really know how much strategy really exists in solitaire, but I was playing it a lot, apparently.
My mom's addicted to solitaire. How are you addicted to solitaire?
Isn't that fun?
I mean, it's pretty fun. Guys, maybe I just tried to solitaire.
So I mentioned, guys,
Like solitaire.
when you're asked to construct a sample space or come up with the sample space for an experiment, we saw some ways of keeping track of all those possible outcomes and doing it methodically. Another option is a tree diagram. It's a schematic representation of the sequence of events and their probabilities. It's used to determine all the possible outcomes of a probability experiment. So it's used to determine the sample space. Draw a tree diagram for 2 flips of a coin and write the sample space. You can set up tree diagrams horizontally or vertically. Depending on the amount of paper I have, I will adjust. But I like to work from left to right as opposed to top to bottom or bottom to top. So the first thing I'm going to do is list all of the possible outcomes for the first flip of my coin. What are the possible outcomes for my first flip? Let's say the first flip landed on heads. What are then the possible options for the second flip? Still heads or tails? What if my first flip landed on tails? What are the possible outcomes for the second flip? Heads or tails? Now, this was asking us to draw a tree diagram for 2 flips. You can see how we can continue to build on this if it asks for 3, 4, 5, however many flips, right? You just keep adding the next one. Now, the other thing that I talked about, and we'll have more conversations about this next week, I always started with, if my first coin landed on heads, what are the possible outcomes for the next coin? Now, both options existed regardless of what that first flip landed on, right? We're talking about what that means, and there's some terminology with that. But that's not always the case. Okay, if my first trial or event occurs one way, that could impact the second. Okay? So things to be thinking about. So we drew our tree diagram, and from this tree diagram, we can write the sample space. This represents and gives us an idea. It's a tool that we can use to write the sample space, but this is not the sample space. The sample space is written as a set with all the possible outcomes listed individually. Each unique branch of your tree diagram represents a unique possible outcome of that experiment. So those lines connect branches. So my first branch goes heads, heads. My second branch goes heads, tails. My third tails, heads. My fourth tails, tails. Maddie, do you have a question?
Do you draw a tree for all possible, like, now you would do another one to the right of like heads, heads, then heads, 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 heads?
I don't understand your question.
Wait. Oh, I don't. Never mind, I figured it out.
Okay, okay. If something else comes up, like, make sure you ask.
Okay.
Nicole, question?
I was just gonna say I could answer her question, I know what she was thinking.
Oh, what was she thinking?
At least to me, what you were asking is you would draw another bracket from the page and you put another page in it, in a.
Yeah.
Oh,
But
from
now
here,
I'm
keep building?
Yeah, but now I'm seeing they're like, reversible too, like it could be heads, then. I don't know what I'm talking about, I'm confused.
So make sure you're clear on what the experiment is. So the experiment is flipping 2 coins. So here's my first flip, here's my second flip. If I continue to build, then I'm including a third flip.
Oh, okay.
Okay, so each of these represents each time the coin is flipped. Now, you made a comment, and I just want to address that. When we first looked at this, we could flip heads and then tails. We could also flip tails and then heads. That's right here.
I got it. Yeah.
Cool. So my sample space has heads, heads, tails, tails, heads, tails, tails. It's important to note the tree diagram is not the same thing as the sample space. The tree diagram is a tool that we use to identify the sample space. The tree diagram can also be used to find probabilities, but we'll talk about that later. Questions? Let's draw a tree diagram to find the sample space for the gender of 3 children in a family. So we're looking at the gender of 3 children. What are the possible outcomes for the first child? What's that? Boy or girl? What about the second child, given that the first child was a boy? Still a boy or a girl. The gender of the first child doesn't seem to be having any impact on the gender options for the second child. So what if the first child was a girl? Still a boy or a girl. What if the first 2 kids were boys? What's the possible gender for the third child? Still a boy or a girl? What if the first child was a boy, the second child was a girl? Still boy or girl for the third child? Is that going to change at all? No. Using this tree diagram, let's get the sample space. Each unique branch represents another possible outcome. So starting with from left and going to right, our first branch goes boy, boy, boy. What's our second branch? Boy, boy, girl. Watch up here, guys, for a second, please. Thanks. Our third branch, boy, girl, boy. Our next branch, boy, girl, girl. Girl, boy, boy, girl, boy, girl, 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 boy, girl, girl, girl. Questions on how to read the tree diagram to identify the sample space? Awesome. All right, let's list it out. Yes, ma'am.
Does the arrangement of the sample space matter?
Not particularly. As I mentioned before, if we're not systematic at all, we run a higher risk of missing outcomes. But no, unless there's like some order that seems pretty obvious, such as the example when we listed the sample space for the rolling of a die.
It's like the way I did it, instead of doing 4 across, I did 4 down.
Oh, in terms of just the structure of it? No, I don't care.
Okay.
I don't care. Formally, this is how we write it with everyone separated by a comma. However, if you saw in the last one when we did the flipping a coin 3 times, I just listed them vertically. I'm not super concerned about that.
Okay.
An event consists of all the outcomes of a probability experiment or a subset of the sample space. I'm sorry, consists of a set, not all of them. It's written using capital letters, so we're talking about some notation. We usually use capital A, B, C, D to represent our event. We'll talk about syntax and how we write things out as we go. P with the parentheses, then A on the inside, is read the probability of event A. To distinguish between experiment, sample space, events, the experiment is rolling a single dice. The sample space is all of the possible outcomes of rolling that. So 1, 2, 3, 4, 5, 6. Our event could be rolling a 6. That could be the event of interest that we're looking at. Another possible event could be rolling an odd. So 1, 3, 5. An event is not necessarily one individual outcome. It could be a subset of those outcomes. When we talk about calculating probabilities, there's two methods. We have the classical method and the empirical method. So let's look first at the classical method. The classical method uses the sample space to determine the numerical probability that an event will happen. It assumes that all of the outcomes in your sample space are equally likely.
Sorry, so when you had the event rolling a 6, and then you did a 6 in there, did it mean like there's only one time that you're gonna roll a 6, or you could roll it 6 times? Like, what does the 6 in that mean?
We're just denoting a set of outcomes that are included within that event. So the braces are talking about a set of values or a set of outcomes. The sample space is a set of all possible outcomes. This set is the set of outcomes for this particular event. This set is the outcomes for this particular event.
So you're not numbering like how many times it
Nope.
happens? Okay.
Nope.
Gotcha.
Again, that classical method, it's based on our sample space, so all of the possible outcomes, and it assumes that all of the outcomes in the sample space are equally likely. Equally likely events are events that have the same probability of occurring. To calculate the probability using the classical method, again, our notation, the probability of our event E, we use a capital E for event a lot. Just like when we were solving equations in algebra, we used X as our variable all the time. This notation, N of E, is the number of ways that E can occur. N of S is the total number of outcomes. So it's the number of outcomes in your sample space. This ratio right here is the way that we typically think about probability. We don't think about it symbolically. We think about it in terms of the number of ways that your event can occur over the total number of outcomes. We will think of this formula kind of as like a mantra throughout this chapter. When you're stuck trying to figure out probability, ask yourself this: how many ways can my event occur, and how many possible outcomes are there? And work with them individually. Don't try to put them all together. Using a deck of cards, find the probability of getting a queen. As I mentioned, we'll talk about some syntax and ways of writing this. The event is a queen, so I might use Q to name my event, because we're talking about queens. To find the probability of getting a queen, it's the number of ways that we can get a queen. So how many cards in the deck are queens?
Four.
There are 4. How many total cards are in the deck? 52. Probability can either be represented as a fraction or as a decimal. If you're leaving it as a fraction, you need to simplify that fraction. What is 4 over 4 over 52 simplified? 1 over 13. When you're working on my stat lab, it'll tell you in blueprint below that answer field whether they want that answer as a fraction or if they want it as a decimal and how they want it rounded to. Depending on what the experiment is, they may be more likely to ask for a fraction or a decimal. When dealing with cards and simple events like this, probably going to be asked to leave it as a fraction. As we get more complex events, then we might start looking at decimals. Okay? Follow those directions. Let's look at C. I don't really know how to abbreviate a black 4, so I just wrote out black 4 as my event. I have found that in certain problems, by giving a more explicit description of my event, helps me figure out what I'm actually doing. What's the probability of getting a black 4? So we think about how many black 4s are there in the deck.
2.
What are they?
Spades and clubs.
2 of spades and 2 of clubs. How many cards are there in the deck?
52.
What does this simplify to?
1 over 22.
Good. Let's jump to E. What is the probability of getting a 3 or a diamond? So I want you to think about this one on your own, and then we'll talk about it. First, we need to figure out how many cards in the deck are a 3 or a diamond.
17.
Okay, so I think I heard 3 different answers. Maddie, you said 15?
Yeah, there's 4 3s and then 13 diamonds, but then there's a 3 of diamonds, so that would.
Okay,
I said 16.
16, and then I know,
Well, I said
17?
17, but then that factor makes it so there's 16 possibilities.
okay, so good. Let's think about this, okay? Or is one or the other, right? Or both. In our everyday language, that word or, we use it as something called an exclusive or, meaning one or the other, not both. You can either have pizza or a hamburger. You cannot have both. Okay? You can either take stats or you can take liberal arts. You cannot take both. That's what we think of when we use the word or in our everyday languages. In math, it's an inclusive or, so it's one or the other or both. So thinking about this, how many 3s are there? There's 4 3s. How many diamonds are there? 13. But one of those diamonds happens to be what? The 3 of diamonds, which I've already counted in the 4. Can I count that 3 of diamonds twice? No, because it doesn't exist twice in the deck. So let's write ourselves a little note about this. So we know we've got 4 3s and 13 diamonds, but one of those diamonds is also a 3, and we can't count that card twice. So we're going to take one away. If you flip a coin 3 times, find the probability of getting all heads. Notice when I'm starting my probability statement, I generalize and I just use E to describe the event that we're looking at. That's another option. I don't really care how you name your event. Okay? I will tell you that you want to get into the habit of writing probability statements formally. So rather than just putting the answer down, write it as a statement. The probability of our event equals what? How many outcomes result in all heads?
1.
How many possible outcomes are there? Good. For B, I'm going to add another word here. Let's find the probability of finding exactly 2 heads. That should be implied, but I know some people have argued that with me. So I'm going to make it explicit. What is the probability of getting exactly 2 heads? There are 3 outcomes that result in exactly 2 heads over 8 possible outcomes. The classical method for finding probability utilizes the sample space. In the last 2 examples, we've seen that there are certain experiments that we are just familiar with the sample space off the top of our head. Rolling a die, drawing a card from a standard deck of cards. We know that sample space very well, so I don't need to see it in order to be able to answer these questions. However, if I were to ask you guys, what's the probability of getting all heads when flipping a coin 3 times, without this sample space, we may not be able to come up with the answer very quickly. So there are times where you're asked to find a probability for a certain experiment. If you cannot figure out where to go initially, start by trying to make the sample space. Okay? If you can see all the possible outcomes, then you can find the probability. Now, what's the technique that we've learned as far as finding the sample space goes that maybe makes it a little easier?
Tree diagram.
Tree diagram. Okay, so if you're stuck on a probability and you're like, I don't know, try a tree diagram. It might get you somewhere. Some rules of probability. The first, the probability of an event is a number between 0 and 1. Again, it can be represented as a fraction or a decimal. You're going to read the directions to know how to write your answer. There's no negative probabilities, and there's no probabilities greater than 1. This is something you guys want to think about because it's a really easy check. If you get a probability that somehow is greater than 1, and we'll see some problems where that's possible, not really actually possible, but if you're doing it wrong, you could possibly get a number larger than 1. That should be your red flag, right? It's not reasonable to get a probability larger than 1. If an event cannot occur, the probability is 0. An example, when rolling a single dice, what's the probability of getting a 7? 0. There are 0 possible outcomes that result in 7, and there's how many possible outcomes? 0 divided by 6 is 0. You don't need to formally write that fraction 0 over 6 out. If you know that the event is impossible, write 0. An unusual event is an event that has a very low probability of occurring, not necessarily impossible though. So be careful when you start assuming things being unusual versus a probability of 0. If an event is certain to occur, then the probability of that event is 1. For example, when rolling a single dice, what's the probability of getting a number less than 7? How many outcomes are less than 7? How many possible outcomes are there? 6 over 6 is 1. The last property when we're talking about probabilities is that the sum of the probabilities of all of your possible outcomes, so all the outcomes in the sample space, is always going to equal 1. So using that example of rolling a single dice, we know our sample space to be 1 through 6. What's the probability of rolling a 1? 1 out of 2. Probability of a 2? Probability of rolling a 3? Probability of rolling a 4? 5? 6? If I add up all these probabilities, what do we get? 6 over 6 or 1. The sum of all of the probabilities for all of your possible outcomes is always equal to 1. More on unusual events. So an unusual event is an event with a low probability of occurring. Typically, an event with probability less than 0.05 is considered unusual. So that's the threshold that our textbook uses. Depending on the statistician, that value might be different, but for our book, for our homework, an event that has a probability less than 0.05, so not equal to 0.05, but less than 0.05 is going to be unusual. Next, we're going to look at a different way of calculating probabilities, and this is using the empirical method. The empirical method relies on experience to determine the likelihood of events. It counts the number of times that an outcome has occurred in a number of trials and writes it as a proportion or fraction or decimal. So the probability of our event is F over N. F is the frequency. We've seen this variable. N is our sample size. Frequency is the number of times that event occurred, N is the number of trials. We're going to use this formula or the empirical method to find probabilities when we are given data or the results of an experiment. Suppose when playing a board game, you have a spinner with 8 spaces, all the same size. When playing the game, you decide to count how many times any person has spun a 5. At the end of the game, there were a total of 179 spins, and 39 of them were a 5. Find the empirical probability of rolling a 5. Again, when we think about empirical probability, think about it in this sense, okay? Not that the symbolic formula isn't meaningful, but the way that we interpret it is going to be more important. So in this experiment, how many times did a 5 occur?
39 out of over 39.
The 5 occurred 39 times, and how many trials were there? 179. Now, this is an example where if I was going to put some money on any type of bet, my stat lab's probably going to ask this as a decimal. This is kind of an unattractive fraction. Less attractive fractions are more likely to be asked as decimals. Okay, not always, but sometimes, most of the time. If I were to round this decimal to 3 decimal places, what would be my probability?
0.218.
Good. Would this event be considered unusual?
No.
Again, that threshold that we're going to use is 0.05. So only if our probability is less than 0.05 will we consider the event unusual. Now, one quick comment. This problem said find the empirical probability. So it gave you an indication of what type of probability, what formula you should be using. Do not expect that. Okay? The questions are just going to ask, find the probability. And based on the context of the problem, you have to figure out what method you're going to use. If they're giving you the results of an experiment like they have here, you're using empirical probability. If they are not, you are using that classical method. The classical method, and I will sometimes interchange it, is also called theoretical probability. So if I say theoretical probability, that's what I'm talking about. Okay. But if they give you data, if they give you the results of an experiment, you're using that empirical probability. My guess is that most of us will probably figure that out very, very quickly. It will seem intuitive. Okay? Suppose you did a survey to determine if people like the taste of a new soft drink. Below are the results. What is the probability that a person responded no? There are 8 individuals who said that they do not like the new flavor or the new taste. And there were 25 total people in the survey. What is this probability as a decimal?
0.82.
Good. Questions?
Yes, will you specify on like the exam or the quiz whether you want it in a fraction or a decimal or?
If I don't specify, then I don't care. Most of us will start with a fraction because that's how we set up probabilities. So when I'm looking at your work, I'm looking at that initial fraction, making sure that you've set it up correctly, you've identified the correct number of outcomes over the total. But either it will specify explicitly or it will not matter. As you've seen in the test and the last couple quizzes, in the directions, it'll indicate how we want you to round in general. Now, you will find that there are going to be certain cases where we change that up. So it is really important to read the directions and be mindful of rounding. Okay? So maybe it'll say, round to 3 decimal places unless otherwise noted. So there might be problems within the quiz or test that say, all right, we want you to round this answer to 4 decimal places. That doesn't change the overall directions, it just changes it for that one problem. In a sample of 50 people, 21 had blood type O, 22 type A, 2 had type AB, and 5 had type B. Set up a frequency distribution to find the following probabilities. We should be very familiar with frequency distributions. That's what we talked about all in chapter 2. So we list our categories, or in this case, the blood types. We get O, A, B, and B. What were their corresponding frequencies?
29, 22, 2, 5,
What's the total?
50.
Good. What's the probability that a person has type O? There are 21 people with blood type O, 50 total people in the study. If I were to write this as a decimal,
0.42.
good.
Just to be clear, would you prefer it to be P-O?
I don't care.
Okay, you don't care. Okay.
I really don't care.
Sure.
You know what I care about? That you have this part. This makes an entire probability statement. That does not. That's just an answer. I want you guys training yourself to write that entire probability statement. I'm training you now so that when we get into chapters like 10 and 11, and we're like, yeah, you must write your probability statement. You're used to doing that. Because at that point, then it will make a big difference, and then, you know, we just don't want to be learning that lesson the hard way at that point. So train yourself now. But how you name your event in that symbolic form, I don't care. What's the probability that a person has type A or type B blood? So I'm going to switch up now. I'm going to say A or B. And Alicia, coming back to that question, I will switch it up depending on what I'm trying to do, and I will start recognizing weaknesses in myself. So there are times where I need to see it written out in order for my brain to process what I'm supposed to do.
Okay.
If I know exactly how I'm setting it up and I don't really need a whole lot of details in that event description, then I'll just use E. But again, I don't really care. You guys will start finding where you guys have your own hurdles and challenges, and you can address them on your own based on that. Blood type A or blood type B?
27 over 50.
How do we get 27?
You add both A and B together.
So there's 22 people who had blood type A and 5 people who had blood type B. So a total of 27 people with A or B. Now, thinking back to that problem that we saw before, the probability of getting a 3 or a diamond, we had to do some subtraction. We had to take one away, right? Because when we thought about the 4 3s and the 13 diamonds, there was one that was counted in both of those, right? Well, none of these 22 people are also in this group, and none of these 5 people are also in this group. What is this as a decimal?
0.54.
Excellent. What's the probability that a person is neither type A nor type O? So I'm going to go back to E because I don't know how to write neither A nor B shorthand. If that doesn't illustrate the point that I don't really care. I don't know what it does. 7/50? So if we're neither blood type A nor type O, what are we?
It's B or AB.
B or AB, right? So there were 2 people that were blood type AB, 5 people that were blood type B, and that's decimal is 0.14. Questions? The following data is the hospital stay for maternity patients. We're not going to go through these examples all the way through, but I do want to make sure we talk about the language and how that sets up the possible outcomes for the event. So looking at B, we want to find the probability that a patient stays less than 6 days. What outcomes are included in that event?
5, 4, 3. Or sorry.
It doesn't, I mean, I see what you're doing, it's fine. But less than 6 days, that includes outcomes 3, 4, and 5. What about at most 4 days? What does at most 4 mean?
3 and 4. They didn't say more than, but they say
Greater than or
equal to.
Less than or equal to. At most is equivalent to less than or equal to. At least 5 days.
So 5 or above,
So 5,
or 2 or 7.
5, 6, or 7. At least is equivalent to greater than or equal to. A trick, if you notice yourself getting caught up on that language, the at least, the at most language, those less than is not typically an issue, but these two are sometimes problematic, right? If you notice that you're getting caught up, pause, remove yourself from the problem, and come up with a sentence or a scenario using money with that language. I can spend at most $5. What does that mean I can spend?
I don't know, up to 5.
Up to $5, or I can spend $5, right? 5 or less. I need to sleep at least 8 hours a night. What does that mean I need as far as sleep goes? 8 or more hours. Well, that wasn't really a money example, but the point is, if you can kind of remove yourself and put yourself in a more relatable experience with those phrases, you might be able to figure it out a little bit easier, okay? We get hung up with thinking already about probabilities and less about what that means. So remove yourself from the problem for a moment, make sure you're clear on that language, and then go back and say, okay, now that I understand what at least means or at most means, now I can set this up. The law of large numbers. As the number of trials of a random phenomenon increases, the proportion of occurrences of any given outcome approaches a particular number in the long run. Now, we're going to translate this, so what this means to us. The law of large numbers is describing the relationship between empirical probability and classical probability. Empirical probability, remember, is based on data, right? The results of an experiment. Where the classical probability is just based on the possible outcomes. So, for example, and well, let's look at, I'm going to use flipping a coin, but we don't need to look at that example. What is the probability if I flip a coin that it lands on heads? 0.5. Okay. Careful with automatically translating probabilities to percents. They are related. Sometimes they'll ask you for percents, but if they ask you for a probability, it's not appropriate to give the answer as a percent. So just be mindful of the difference. So if I flip a coin, the probability that it lands on heads is 0.5. Now, what that tells us is that half the time we should get heads, right? If I flip a coin 10 times, am I always going to get 5 heads and 5 tails?
No.
No. And in fact, it's pretty unlikely. If we were all going to do that exercise, I bet very few of us would actually get 5 and 5, if any. But what the law of large numbers says that if I take those 10 flips and I increase that number of trials, so let's say I look at 1,000,000 flips, what we'll see is the empirical probability of landing on heads begins to approach the classical probability. So as we increase the number of flips, that empirical probability is going to get closer and closer and closer to 0.5. There is a phrase in our problems that's pretty common that indicates that they're asking you about the law of large numbers. That phrase is in the long run. So the example is, we flipped a coin 20 times, we got 16 heads and 4 tails. So they're describing an experiment, but they're asking you in the long run. So if I were to continue flipping the coins, what would you expect the probability of heads to be? It's no longer going to be the 16 over 20 like based we have on the empirical probability for this experiment. In the long run, that empirical probability is going to approach the classical probability of a head. What's the classical probability of getting heads? What's the probability? 0.5. Now, an extension of that, Nicole, and you'll see this on my stat lab, they'll say, how many heads do we expect to get then? And that's when we take that probability and multiply it by the number of trials. Again, that phrase, in the long run, that's cueing you that, oh, we're using the law of large numbers for this problem. Last thing we're going to talk about are subjective probabilities. A subjective probability is the degree to which a given individual believes an event will happen. We use subjective probabilities all the time. All the time. A subjective probability is still a probability, so it still has to be between 0 and 1. And it must be coherent. In other words, the personal probability of one event cannot contradict the probability of another. So, for example, we're talking about the probability of finding a parking spot downtown on Saturday afternoon. I believe that the probability of me finding a parking spot downtown on Saturday afternoon is 0.2. What does that mean the probability of not finding a parking spot must be? 0.8. Okay? I couldn't have a probability of not finding a spot being 0.9 because I'm either going to find a spot or I'm not going to find a spot. Those are the only two possible outcomes. Agreed? What's the sum of the probabilities of all possible outcomes? 1. Questions? Fantastic.